Hello everyone, I am Bappa Saha, EC third year. Today I am going to present pulse code modulation. Starting from the block diagram of pulse code modulation. Pulse code modulation is basically a process to convert the analog signal into a digital signal, which is some binary numbers like 01011010. At first, the message signal xt is passed through a low-pass filter to discontinue the high-frequency signals by limiting the bands. Now the signal is passed through a sampler to sample the signal, and we will get a flat top pulse amplitude modulation analog signal. Now this PAM analog signal will be passed through the quantization process, and we will get the quantized pulse amplitude modulation analog signal. Now to convert this analog signal into digital signal, we will use an encoder which generates a binary code for every sample. Now we will get the pulse code modulation signal, which is a digital signal or a binary coded signal. Now before reaching the receiver side, this digital signal is passed through many regenerative receivers or repeaters, which are present in between the transmitter and the receiver. These repeaters regenerates the signal, which is not possible in analog signal, and reduces the noise further. Through the channel, the signal reached to the receiver side. Here some noise is present with the PCM. To remove the noise, the signal is passed through regeneration circuit, and we get a clean noise free PCM. Now to convert the digital signal into analog signal, we use decoder and get quantized PAM or pulse amplitude modulation analog signal. Finally, to get the original signal, a reconstruction filter is used there, and we get the original signal xt, which could be a voice message or an image or anything. Now let's talk about the quantization process. Quantization means approximation. By quantizing the PAM pulse, original signal is approximated. Quantization discretized the amplitude of continuous PAM samples. Since the original signal can have an infinite number of signal levels, the quantizing process will produce errors called quantizing errors or quantizing noise. Now taking a sample signal, we can understand how quantization works. This is a signal xt which is divided into 8 quantization levels. Every level has a step size s, and every quantization level is presented by delta. Step size is Vh minus Vl by Q, where Vh is highest voltage of the signal and Vl is the lowest voltage of the signal, and Q is the total number of quantization levels at center of step means S by 2. Q0, Q1, Q2 Q7 are placed. For all values of xt in range of delta 0, output is Q0. Similarly for Q1, for delta 1 Q1, delta 2 Q2, means any value in the range of delta 0 will be considered as Q0. Now quantization noise or quantization error. Here we are taking the approximate values of the signal. So the difference between the original value and the approximate value is called the quantization error. Now bandwidth of PCM. Let the quantizer use V number of binary digits to represent each level. Then the number of levels that can be represented by V digits will be q is equal to 2 to the power v. Here q represents total number of digital levels of FL level quantizer. Each sample is converted to v binary bits, that is number of bits per sample is equal to v. We know that number of samples per second is fs, where fs is greater than or is equal to the maximum frequency of input signal. Now number of bits per second is equal to number of bits per samples into number of samples per second, which is v into fs. Now the number of bits per second is also called signaling rate of PCM and is denoted by R. So the signaling rate in PCM R is equal to v into fs. Now bandwidth needed for PCM transmission will be given by half of the signaling rate, which is bandwidth is less than or is equal to 1 by 2 R, or bandwidth is less than is equal to 1 by 2 VFS, or bandwidth is less than equal to 1 by less than equal to VFM. Now if we want to reduce the quantization error, we have to reduce the step size. That will increase the quantization level, and that will increase the bit rate, and that will increase the bandwidth. So the quantization error is related to bandwidth. If we want to decrease the quantization level, the bandwidth will increase. Now SQNR of PCM, signal to quantization noise ratio. The signal to quantization noise ratio of the quantizer is defined as S by N is equal to normalized signal power by normalized noise power. If type of signal at input, that is xt, is known, then it is possible to calculate signal power. When load resistance R is equal to 1 ohm, then the noise power is normalized, that is normalized noise power is equal to mean square V noise by 1 is equal to del square by 12, where del is step size. Let assume that input xt to a linear quantizer has continuous amplitude in the range of minus x max to plus x max. Therefore total amplitude range is x max minus x max is equal to 2x max. The number of bits v and quantization levels q are related as q is equal to 2 to the power v. So the delta is equal to 2x max by q is equal to 2x max by 2 to the power v. Now the s by n is equal to p by del square by 12, which is equal to p by 2x max by 2 to the power v whole square into 1 by 12, which is finally 3p2 to the power 2v by x square max. Now expressing the signal to noise ratio in decibels, S by n dB is equal to 10 log 10 S by n, which is less than 10 log 10 into 3 into 2 to the power 2v, which is less than is equal to 4.8 plus 6v decibel, where v is the number of bits. Signal to noise ratio will be, signal to quantization noise ratio will be S by n is equal to 3 into p into 2 to the power v, where p is destination signal power. Now SNR is more better, but there is a trade-off between SNR and bandwidth. If we want to increase the SNR, the number of bits will increase and the bandwidth will also increase. So that's all about pulse code modulation. Thank you.